Our next talk is by Nashlen and Govindasamy on lower bounds against the ideal proof system in finite fields. Nashlen, please.
Thank you. So this is joint work with Tal Elbaz, Jiaqi Liu, and Ido Samaret, who are all also at Imperial. Before we get into some of the details, let's take a look at an overview of the main results. So our first main result is a superpolynomial lower bound against constant depth multilinear IPS over finite fields. Next, we prove a separation between constant depth multilinear IPS over finite fields and its large fields counterpart. And finally, we show a translation where we can move from algebraic instances to CNF instances, which is more interesting in the propositional proof complexity setting. So the ideal proof system is an algebraic proof system, and these stem from Hilbert's Nashlen sets. This says that if you're given a family of polynomial equations that have no common Boolean solution, then there exist polynomials gi's and hj's such that we have this polynomial identity, namely that one is in the ideal generated by our axioms, including the Boolean axioms. Conversely, if you're given this polynomial identity, then it shows that our family of polynomial equations have no common Boolean solution because the left-hand side would evaluate to 0. And so this identity can be seen as a proof that our family of polynomial equations have no common Boolean solution. The Nashlen-Stotz proof system measures the size of this proof as simply the number of monomials in the gi's and hj's. But the stronger ideal proof system introduced by Grocha and Patasi uses more succinct representations for polynomials. And here the proof size is measured as the circuit size of the gi's and hj's. So in this work, we prove our bounds against constant depth multilinear IPS then prime. But for this talk, it's suffices to think of this as meaning that the gi's are constant depth and multilinear, but the formal definition is slightly more general. And indeed, the formal definition of IPS is slightly more general than what I presented earlier. So here we see the ideal proof system relative to other commonly studied proof systems. In the left column, we have the algebraic proof systems, which we looked at earlier. And in the right column, we have propositional proof systems, where the proof lines are propositional formulas. And an arrow from a proof system to another indicates that the formal proof system is simulated by the latter. And as you can see, the ideal proof system is a fairly strong proof system that simulates many of the commonly studied proof systems. With regards to propositional proof systems, we have the so-called Cook's program, which aims to prove superpolynomial lower bounds against stronger and stronger proof systems, with the ultimate aim of settling some fundamental open problems in complexity theory. However, for the moment, we only know superpolynomial lower bounds for the proof complexities that are below this red line. And here, AC0 Frege is a proof system where the proof lines are constant depth formulas. And AC0 P Frege is the analogous proof system where we are allowed to use mod P counting gates. It is sometimes thought that AC0 mod P Frege lower bounds are within reach of current techniques, especially because we have these lower bounds for AC0 Frege, and because we have AC0 mod P circuit lower bounds. But these results have all been obtained in the 80s, and superpolynomial lower bounds against AC0 mod P Frege still remain elusive. But in the work that introduced IPS, Grocha and Patasi also showed that constant depth IPS over Fp simulates AC0 mod P Frege. And so proving lower bounds against constant depth IPS over finite fields may provide some insights to the long-standing open problem of lower bounds against AC0 mod P Frege. So we have some previous constant depth IPS lower bounds. In previous joint work with Hakoniemi and Samaret, we were able to prove superpolynomial lower bounds for the same proof system that we look at in this work. However, there it was required that the field had characteristic 0. And later, Hakoniemi, Lemay, and Samaret were able to improve on this result by allowing individual degree of log n. But again, the field needed characteristic 0. And independently and concurrently with this work, Behera, Lemaya, Ramanathan, and Srinivasan proved a superpolynomial lower bound for the same proof system as this work, and also over positive characteristic fields, but they require the field size to grow. So now we turn to our first main result. And if you're given a field of characteristic P, where P is some prime, which is at least 5, then every constant depth multilinear IPSLN prime refutation of the knapsack mod P instance over F requires superpolynomial size. Our proof strategy is similar to the strategy used in GHT to obtain the IPS lower bound. So we start with some instance, and if we had a circuit lower bound for circuits computing the multilinear polynomial that equals to 1 over the instance of a Boolean assignments, then we can use the functional method of Forbes, Spilka, Samaret, and Vigdisson to obtain the IPS lower bound. And if we had set multilinear circuit lower bounds for the set multilinear circuits computing the set multilinear projection of F, then we can use the set multilinearization result of Lemaya, Srinivasan, and Tavernet to obtain the circuit lower bound. And if we had a rank lower bound for the coefficient matrix of the set multilinear projection of F, then we can use another result of LST to obtain a set multilinear circuit lower bound. So it remains to move from the hard instance to the rank lower bound. And in GHT, the hard instance, the knapsack instance, is constructed such that it embeds subset sum instances. And now we use the full degree lower bound for refutations of the subset sum instances to obtain the rank lower bound. But over finite fields, we face some obstacles. For one, the hard instance isn't unsatisfiable. And for good measure, the set marginalization result of LST does not hold over finite fields. In this work, we try to remedy these obstacles. We use the recent set marginalization result of Forbes, which holds over all fields. We also construct a variant of the knapsack instance, which we call the knapsack mod P instance. And this instance embeds not simple subset sum instances, but subset sum-like instances, which we prove a full degree lower bound against the refutations to obtain the rank lower bound. And going from, so the LST relation from the rank lower bound to set multilinear circle lower bound still holds over finite fields, but we use the improved parameters of Bhargav, Dutta, and Saxena. So we will not explicitly construct the knapsack mod P instance here, but hopefully this slide can provide some intuition on how it is constructed. So in GHT, we use the knapsack instance is constructed over a word where each index of the word wi is illustrated as a box of width wi, and each binary string of length wi corresponds to a variable. So the positive indices are represented by these blue boxes, and these hold the positive variables, while the negative indices are represented by the red boxes, and these hold the negative variables. And GHT uses how these boxes overlap to construct the instance. So here, these FIs are polynomials in the y variables, and on Boolean assignments to the y variables, we obtain the subset sum instance for which we have full degree lower bounds. But for this work, we use a scattered partition of the positive indices. And a scattered partition is where of the positive indices where two positive indices are not in, two positive indices in the same part do not share a common negative overlap. So the illustration shows an example of a scattered partition. The parts are listed above the blue boxes, and the negative overlaps are illustrated below the red boxes. So the scattered partition is needed so that the knapsack mod P instance is multilinear. And KSWPI is a Boolean function. Its construction such it is a Boolean function. And so that when we take the sum over the R parts, KSWP ranges from 0 to R. So if we have fewer parts than the characteristic, there can always exist a beta such that KSWP is unsatisfiable. Finally, KSWPI is constructed such that when we have Boolean assignments to the y variables, we obtain these subset sum-like instances for which we prove full degree lower bounds. Our next result is a separation. And here we show that for the symmetric knapsack, so for a given field of characteristic P, which is at least 3, the symmetric knapsack has no satisfying Boolean assignments over that field or over any characteristic 0 field. Moreover, over F, the symmetric knapsack has polynomial size refutations, but over characteristic 0 fields, every refutation of the symmetric knapsack requires superpolynomial size. So the symmetric knapsack is a variant of the knapsack instance used in GHT, but here we embed elementary symmetric sums of degree 2. And the upper bound can easily be seen by using a simple application of Fermat's little theorem. And to prove the lower bound, we need to, since the symmetric knapsack embeds elementary symmetric sums of degree 2, we need to prove a full degree lower bound for this. And we obtain this, and then we obtain the rank lower bound, and then ultimately the IPS lower bound similar to GHT. And so our final main result is a translation. So it should be noted that in IPS, the lower bounds are proved over purely algebraic instances. But here we show that any lower bound against any proof system, at least as strong as constant depth IPS over finite fields, for any instance, can be translated to a CNF formula for the corresponding IPS fragment. And what this means is we've known from Groch and Pitassi that constant depth IPS over FP simulates AC0 mod P Frege. But a lower bound for constant depth IPS over FP wouldn't necessarily imply a lower bound for AC0 mod P Frege, because we need to insist on the instance being a CNF instance. But here we show that for any instance, even a purely algebraic instance, we can get a CNF instance. And so any constant depth IPS lower bound over FP would imply an AC0 mod P Frege lower bound. The caveat is that the translation uses non-multilinear constructions, whereas our lower bound is for multilinear IPS. And so ultimately, the problem of proving superpolynomial lower bounds against AC0 mod P Frege remains open. Thank you.
Do you have time for questions?
Before the translation, can you say something about the parameters of the new CNF formula you construct? Like what does it look like in terms of the original thing, or like the size of the formula?
So for the translation, we try to mimic the sort of the instance in CNF of the hard instance with like the gate by gate simulation in the CNF formula, and like I'm not sure entirely of the parameters. I haven't checked it, but like the important parts of it not being multilinear is there, and like it mimics this Santanem-Somret early translation where they use additional axioms, but because of this constant depth IPS, we can show that it's strong enough to get to those additional axioms. So we don't use additional axioms. They are, nothing particular that blows up in the thing. And it's quadratic in the degree,
No, quadratic is the number of, you have a circuit, is the number of subformulas. If you see the subformula.
Let's thank the speaker again.